2-hour portion, but given the background, I shifted and did a bunch of extra stuff on networking this morning. And so this will be a little bit compressed. If you don't get all of this done, then it's still learning material you can continue to use afterwards. But the basic structure here for the next hour or so is, let's see, where are the links? Let's see. So here you will see a GitHub page titled the WQRN tutorial, because the first time we did this was about 3 years ago at the workshop for quantum repeaters and networks, and it has evolved a little bit since then. You will see 2 links here. One that says Open in Collab in English and one that says Open in Collab for the Japanese version. There are 2 versions of this. You can open either one for those of you who are learning Japanese, right? You can try that if you like. If you're particularly sophisticated with Python and Jupyter and such things, you can also just download the files and execute this directly locally on your own machine if you prefer. I am going to open this here, and it will take you to this. And there are a set of instructions here. Each of these is openable and closable things that you can run. It should run directly in your browser, and it runs this Qiskit-based code on Google Collaboratory. So Google Collaboratory is a, he didn't fix that at all, did he, right? I'm just as loud and there's just as much. Is it better? Okay. You can open this up and execute this in each of the cells. So what it does is it loads up the Qiskit library of software for gate-based, circuit-based quantum algorithms and operations. And then we're going to use this just in a very simple calculation and demonstration mode. Qiskit, of course, can also actually be used to connect directly to real IBM machines and also machines from some other vendors. But we're not going to do any of that. This is all directly just simple simulations. So there are 3 basic sections to it. Well, 4, including the introduction. So there's getting set up and the basics of quantum gates, and then entanglement and the Bell states, and then teleportation, entanglement swapping, and then purification. And so you're pretty much everybody, I think, will get through this pretty quickly. A bunch of these are just push button. All you have to do is push the button. So literally here, try adding 2 numbers, just to hit the triangle there. Do you want to run it anyway? Yes. And this will fire up a virtual machine at Google, which will run your Python environment. And after it spins for a couple of seconds, then it will finish this, and it will tell you that the glory of glories, 2 plus 3 is 5, right? So for those of you who aren't so familiar with Python or Jupyter notebook execution, this is what it is. There are alternating cells of code and description. And one thing to be very careful about, if you're not familiar with these, is the way Jupyter notebooks are constructed. There's this series of cells that contain this code, and the order of execution is not enforced by the system. So if you scroll to the bottom and you click one of those later cells, it's going to fail with an error because it depends on things that were defined earlier in the notebook, but the system will not enforce that. So you need to execute each of those cells in the notebook as you go. And in particular, this next cell here, this pip install Qiskit, yada, 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 this actually takes a minute or 2 to run. And then there are some helper functions that do all of this. You will need to execute each one of these cells in order. And then the basics of quantum gates. Most of this should be pretty straightforward. So a bunch of these are just click. But then you'll get to some that say exercise, and it says try creating a circuit here. And so you can create your own circuit in that place in the notebook. Then there are descriptions of some of the basic gates and structure of how to do this basic stuff. And then some stuff that will actually draw the circuits for you, and walking through some of these hands-on exercises. And then also one caveat on endianness in Ketzen diagrams, which you should read. Then the entanglement and the Bell states, yada, 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 most of which is pretty straightforward. So you're given the code for the phi plus state, and the exercise is to complete the code for creating the phi minus state, and similarly for psi plus and psi minus. Whoops, that should say psi minus. There's a bug there. And then also the Bell state analyzer and on from there. So this will get you a little bit involved in some of the mathematics and some of the code and notation for those of you who are not as familiar with it, or for the experimentalists who are not as familiar with who might be not so familiar with sort of the simulation environment and things like that. And that's the main thing. And the way we do this when we run this in various workshops, we did this on Saturday for an NICT quantum camp. NICT is the National Institutes for Communication and Technology or something here in Japan. It's roughly the equivalent of portions of the United States FCC and NIST. And they have quantum computing research groups, and they also have an education program. So on Saturday, we actually ran this as a workshop for the 50 or so participants of that. So we've done this quite a bit recently. So this spreadsheet, looks like a bunch of you are in this already. How many people we got? 25 or so. Well, no, 21 or 2 or so are in here. This is not, you're not going to be graded on any of this, but this is just to help you track which things you've accomplished, and it lets us look at where people are and see who's having trouble and who's not. Particularly since we're doing this here in the room and not online, you can also just stick up your hand and say, I need help on this. And let's see, so my team originated this, but some of the most recent fixes to this. How many of you all have used Qiskit? I know I asked otherwise, so 2/3, right? You've probably noticed IBM breaks it every year, sometimes several times a year, right? So there were fixes made to this as recently as a couple of weeks ago to adapt for the fact that IBM keeps changing APIs and things. So it should run in its modern form. And those most recent fixes were thanks to Mia. She actually fixed some of this stuff. So Mia and Soon are my 2 students here who are currently stuck in the middle, and I'm going to ask them to actually get up and wander around the room and help people who are having trouble with this too, because they're actually better at this stage of the stuff actually than I am, and they have both done this this particular notebook relatively recently. So get started, put your name in here. And again, this is just sort of informative to help us as you go and help you as you go. Most of this should actually match up to the topics in the spreadsheet itself. And weirdly, some of these headers seem to have changed a little bit. Am I in the right version of this?
You're the correct one that you sent us.
Yeah, all right. There's some stuff that apparently I missed when I was doing the translation from Japanese to English. But also in the upper portions of this, some of this doesn't look the way it looked a couple of days ago. You will see links to particular videos. And I didn't get around to this morning before lunch pointing out, I didn't get to that last few slides in the QCE slide set. Kaya Namoto, who is one of your sponsors here, she is the head of a thing called the QLEAP Jinzaikse program, the Human Resources Development or Education program or something. And we are subcontractors in that. And within that overall system that is building an online curriculum for quantum computing and communications, my responsibility is the quantum communications. And so we have created a set of courses over the last 5 years that are online. Some of those are behind a closed login system here in Japan, but we also uploaded all of our videos to YouTube. And so those links will take you to YouTube links if any of you actually need some of the stuff here. So this is Mikhail Hajduszek. He created much of the material, and then together we videotaped him in doing the English versions of this, and then I did the Japanese versions of this. So there are both English and Japanese versions of basically all of these. And those are links that will take you into just a subset of that. So if you need additional background, you can pick it up there. And you can store those for later, or you can watch some of them now if you really need to. You can either use headphones or use the subtitles. There are subtitles available in English and Japanese and in several other languages for some of them. Let's see. Anything else? Anything else I need to answer? Let's take about an hour and work on this. And like I said, this was actually originally sort of designed for about 2 hours. So I'm assuming that most of you all will be able to skip through portions of this fairly quickly. But also, if you don't complete it, then we can come back and you can always complete it later, work on it later at your own pace. All right. Have fun. And let me correct a couple of these things that are still only in Japanese. But on Saturday, the visual appearance of this on Saturday was actually different. Let's see. Still need the links? Anybody still need the URLs? Everybody get it? question, this is actually a useful question. What's the purpose of the classical register in this? In Qiskit terminology, you create both a quantum register, which consists of a number of qubits, and a classical register, which is used to hold the results of measurements. And so anything that you're doing, the outcomes of measurements, which can be the outcome of your entire circuit, but they can also be used in feed-forward operations to decide, if I got a 0, then do this. If I got a 1, then do that. So in Qiskit terminology, that's what that's for. So it appears that the video links that are supposed to be active in the spreadsheet have gotten busted somehow, probably when I copied the spreadsheet or something, somehow or another, I screwed something up. So I'm going to work on fixing those, but it'll take me a few minutes to find the right things. How did that get busted that way? In row 8 in the spreadsheet, some of those are supposed to be active links, but they're not. But those were actually supposed to go to the Japanese versions of the videos. The ones in row 6 should still be good links to the English versions. There are, let's see, there may be some in row 6 that are missing. So let me look and see if I can figure that out, see if there's anything actually missing from there. Yeah, for the early columns, I threw L or so. I'm not sure there were actual videos for those, although the green ones in row 8 look like there should be. I don't think we actually have videos for those. So the first actual set of videos that are related to the communication stuff start in column S with entangled states. So on row 6, you should be able to see videos for entangled states, Bell states, no cloning theorem, introduction to teleportation in S through V, and then way out to the right still from there, all the way over at AO, there's a discussion of entanglement swapping. And at AV, from AV through AX, there's a set more on purification and noise. So those are the sets of videos that are linked. For those of you who are not so familiar with Jupyter notebooks, my screen's actually a little small here right now. Let me see if I can widen that where my window is. Oh no, it's still not showing up. All right, back up here. When you start, the very first thing, it should give you a status message up here. Where's my status message? Hugger head visibility. Yeah, over here, so yeah, so the connection to a hosted runtime. Yeah, there we go. So connecting this will tell you, so right now this RAM and disk says I am connected. If you hover the mouse over it, it says I am connected to a Python 3 Google Compute Engine backend with X amount of RAM and Y amount of disk that's available for this. So if you don't see this, or if you see a thing that says connecting, then you're not properly connected to a Google's system, and that's where the problem is. So a couple of people seem both the Jupyter notebook and the spreadsheet, a couple of people have had problems not being able to edit or not be able to get it accessed right. And I think maybe it's some problem with occasional problem with people's internet connectivity. So intermittent problems with that, I think. Kit, when you first create the quantum register, the state should be 0. You shouldn't be able to know that it's zero. I think that's reasonable. Yeah.
Every time I run it, it seems like the output of the measurement is 0.
That's interesting. Get soon to take a look at it. How are people doing? Making progress? Seems like people are concentrating. Yeah, so some people are seeing occasional glitches with the spreadsheet for tracking progress. If you're seeing glitches with that, don't worry about it. Focus on the Jupyter notebook because it's fine. But if you have questions or problems, stick your hand up, and soon or Mia or I will help you out. And of course, they're smarter than I am, so they'll be better at it. There was a good question a few minutes ago. When you're making the circuits for the 4 types of bell pairs, I think the first measurement that it shows you, just the outcome there, it shows you what the probability of the 2 qubits is just in the computational basis. But then as you progress through the spreadsheet a little bit farther, then one of the next exercises is creating the bell state analyzer, which you do with a couple of gates, and then that should give you enough information to actually reconstruct the complete bell pair out of it. So I think we'll go about another half hour with this, and then right about 45 after, we'll switch back into sort of lecture and discussion mode. Yeah, so still gonna do the same thing, isn't it? It's the mic. I have to turn the mic off when I stand close to the window. We on? Yeah. So with entanglement swapping, basically you start with two bell pairs that each span some distance that meet at some junction point. And then what you do is you do the joint bell state measurement on these two qubits. I'll write BSM there on and then you have to communicate the classical results to at least one end of this connection in order to apply correction operators to the qubit in order to correct for that particular projection. One way that I think of this, and when Mikhail and I were developing these online materials, Mikhail said to me, gee, I'd never thought of it that way. But the way I think of this, all the way from the time I first learned this, is that what you are doing is you're taking this qubit and teleporting it to here. So some people view entanglement swapping itself as one of the core primitives of what happens in a network. I view it as teleportation of a qubit that's already entangled with someplace else. They're just two different ways of viewing the same thing that's going on. All right, we'll go another 10 or 15 minutes. So if you all have any questions or anything urgent you want to ask about this, stick your hand up and one of us will help you out with it. A handful of things to know about purification. So this is going to whine when I walk up here. My apologies. Let me shorten this out a little bit. So you start with two bell pairs, right, between the two nodes. You can find this. So this is node A and node B. Now the way I view this, and again, this is just sort of pedagogically a little bit different from the way other people view it, is I view purification as error detection. And some people view it in terms of very mathematical structure of the original state of the larger number of qubits getting shrunk down and purified or distilled to a different state. And one of the world's experts on this overall process is sitting right over there with his hand on his chin. Yes, you. One of the world's experts on this is David. So he can tell you everything you possibly want to know about it. But one of the important things to know about it is, of course, this consumes resources. You start with two bell pairs and afterwards you're down to just one. So again, it consumes more resources. But also importantly, in this structure, you are testing for one kind of error. You are testing, so the way I view this is that you start with a proposition about one of the bell pairs. The proposition of this bell pair is that this bell pair is in psi plus, or phi plus, right? Then what you do with the other bell pair is you use the other bell pair as a test tool to test that proposition. So what you're doing is you do a local C0 gate at each end, and then you measure this out. And so this measurement result should be the parity in the computational basis of these two qubits. And the measurement result here should be the parity of these two qubits. And if the state of those bell pairs was initially the same, you should come up with even parity on both of those. And what that does is it increases your confidence that that remaining bell pair, the bell pair you have left, is in that state that you desire. So that's logically the way I think of it in terms of how it's useful operationally. And you can walk through the math in the density matrix with all of this and sort of see how it falls out. And so some people think of it in those very mathematical terms, but I think of it in terms of those very direct operational terms. Also, the other key thing to know about it, of course, is that, as I said, this is testing the parity of the bell pairs, in this case, in the computational basis. But if you apply Hadamard's in the right place, then you will test the parity in the X basis or the Y basis. And if you're familiar with the block sphere and how errors behave on the block sphere, and this isn't really sort of a perfect analogy, but the way I think of it is, in particular, if you start with a broad spectrum of noise in the systems, what happens in the first round of purification is that you kind of squeeze the error in one dimension, and then the second round of operations, when you test in the opposite axis, you squeeze in the opposite dimension. So you do X purification and then Z purification as a pair. So really you need 4 bell pairs that eventually become 1 in order to test the errors in both X and Z. And that if you have a general noisy state with depolarization in it, that first round of purification, whether it's the X round or the Z round, whichever one you do first, gains you almost nothing in actual improved fidelity of the state, just as that one number. But it squeezes a bunch of the error out of Z error into X error, and then the next time it's going to shrink it a whole bunch. And so the second round, you get a big jump in fidelity. So that's sort of operationally one of the key behaviors of this. And there are a whole set of variants of this purification protocol. This is one of the simplest. This is single selection. There's also what's called double selection purification. And again, in sort of practical or operational terms, one of the things you need to worry about in network design is how you're going to schedule this set of operations when you need to execute multiple rounds of this. How do you decide which bell pairs you're actually going to use for this operation? One approach to doing that is always the tree-based approach, where you start with two pairs here and you purify there, and then you do this. And so that's a straight out binary tree. A different form of the scheduling is what's called entanglement pumping, where you start with this and then you just bring in another base level bell pair that comes from the actual physical system. And so those are two different schedules for the purification. The symmetric tree is the single most obvious and desirable, and it results in the fastest convergence toward really high fidelity if you have bell pairs available. But if you have a slow entanglement generation rate, then while you are waiting for additional bell pairs to arrive so that you can do additional purification, then it results in decoherence. And so in that case, the entanglement pumping approach can be better. You know, some of the people who did, let's see, so tree-based stuff, I think, was in the original Bennett paper on purification, and pumping comes from, didn't Misha Lukin's group define some of that originally? Yeah, you think it's earlier than Lukin's group? Could be. I did all the way back about 16, 17 years ago. We did some work on operationally which of those approaches is better. So in terms of that scheduling, my own group has done some work on that. But the deeper mathematics of how and why purification works, excuse me, that you should ask David and others about. All right. How are we faring? How many people got the basic teleportation stuff done? Good. How many of you got the entanglement swapping stuff done? A smaller number, only about half as many. How many of you also got the purification stuff done? Anybody get that far? A handful of people. Okay. So the purification part then is homework, and I'll expect it on my desk at 8 a.m. tomorrow morning. Right there. I let this go blank, and it didn't come back up. David, my screen went blank. I need to just unplug this and plug it back in.
Maybe. Pumping is Durham Breeder 2003.
What's that?
Pumping is 2003 Durham Breeder.
So David says pumping. There we go. It came back. David says pumping was defined originally in 2003 by whose group? Oh, Duhr and Briegel did it. Okay. So Wolfgang Duhr and Hans Briegel, who are the originators of repeaters, also get credit for the pumping based scheme. One thing about the pumping based scheme is, like I said, it results in slower improvements to the fidelity. It will also saturate. It cannot go all the way to an arbitrarily high fidelity, depending on certain constraints, such as your local gate error rate and things like that. Whereas the tree-based approach can, in theory, basically reach arbitrarily high fidelity. All right. Let's see. I want to pick up for about 10 or 15 minutes here on this, the latter part of these QCE slides. So I'm going to skip over the parts on the actual experimental implementation of Qfly, which I had actually anticipated doing it this morning anyway, because Shota Nagayama will be here tomorrow and he can tell you everything about that. That work is really done in his lab. So I'm going to skip forward in this slide set to page 95 and finish up with this last little bit here. And then I want to talk about standards and standardization, and then we can have a little bit of a discussion. So our basic architecture for a quantum internet is what we call QRNA, the quantum recursive network architecture. And here's a set of references for this, some of the key points on this. This developed out of a whiteboard discussion with a guy named Joe Touch, who worked at ISI, and we've been friends ever since. I was visiting him at ISI at one point, and we had a good conversation about this, because Joe had previously defined a proposed alternative architecture for the classical internet called RNA, the recursive network architecture. And at some point, Joe and I were arguing about something on the whiteboard, because Joe likes to argue. And I was trying to convince him of something, and then all of a sudden, the light goes on, and Joe says, "Hey, that's just like my RNA. That's what I've been trying to tell you." Like, no, it's not what you were trying to tell me. You just came up with it, right? But that's Joe. So the basic idea of a recursive network architecture is that you have a high-level visible topology marked out in each one of these green circles here, and you have that topology that's interconnected. But each node in that topology that you see at one level can be a recursive network inside of it. So this network inside of it would have a set of additional repeaters inside of this, and each one of those repeaters in turn could actually be a recursive network inside. So it's structured much like the classical internet. And I showed you, this morning, a few hours ago, we talked about a 3-level system for that. We talked about the global BGP routing architecture, which interconnects autonomous systems, and then sort of the mid-level architecture, or the network level routing, known as your interior gateway protocol, which is OSPF or ISIS or RIP or interior BGP or what have you. And then the lowest level of the LAN, or local area network routing, which is something like spanning tree. There's no particular reason why you really need 3 separate protocols at each of those levels. You could use the same protocol at each level, and there's no reason to limit it to just 3. And so Joe improved the abstraction in his network architecture and called it RNA. And we then adapted that into quantum structures. And we think this is ultimately a very good way to deal with the fact that routers are going to be short links, and that you need this longer distance entanglement swapping results in the fact that the entire communication session is essentially a distributed computation across the entire network. So you're trying to connect 2 nodes together on 2 sides of the globe. A whole set of repeaters between here and there is going to be involved in this operation. So it's essentially a distributed computation. Well, managing that distributed computation across 100 nodes in a line is not a very easy thing to do, or even 1,000 nodes. And so applying some sort of recursive structure to it results in simplifying that management. And that's the overall goal of this. The 2 key innovations that we think help make all of this work are the rule set based operation and the 2-pass connection setup. The rule set based operation, have any of you all ever heard of a thing called SDN, software defined networking? Oh, 4 or 5 people, that's pretty good actually. So in software defined networking, man, excuse me, my throat today. There's a concept that was developed, depending on sort of where you draw the line, late 90s or early 2000s. And it's essentially an event-driven architecture for a network in which a manager node somewhere defines a small program for each router or switch in the network to execute on each packet that comes through. And so that small program generally does one of four things. I suppose I should write this down, and this is going to cause this to howl again when I come over here to the whiteboard. At every step of, or at every time you hit a router, you're basically, that's not blue. There's a blue cap, but that's not blue. I have blue. It's okay, David, I'm good. At each step, you may either forward a packet, discard a packet, consume a packet, meaning that it's actually delivered to some application software actually running on that node, or ultimately you may also rewrite a packet. And so that means changing some of the headers in it, changing addresses or changing other fields in the packet for whatever reason. And so the forwarding operation is actually sort of noticeably complicated, but I'm not going to get into detail on that at the moment. But with SDN, software-defined networking, you get a structure for defining the set of things. Some of this, there's a particular common approach to this, which is actually falling a little bit out of favor these days, but it's still considered good. OpenFlow, and then a programming language called P4. It's actually fairly common for this. And OpenFlow came out of Stanford University from the lab of a guy named Nick McCune. And I'm not sure actually where the P4 programming language came itself, but it's essentially an evolution of that. And that's the approach that the people in Delft are taking. They're actually using P4 for some of the programming of nodes in the quantum network. Particularly Wojciech Kozlowski was promoting that. So our rule set-based operation was inspired by SDN approaches, but the set of things that we need to do in quantum networks is a little different from this. Because in fact, I said that this is essentially a distributed computation. All of the nodes across the entire chain are involved in creating that end-to-end bell pair. And again, this is in 1G networks, and you'll hear more about 2G and 3G networks later this week. But all of the nodes, intermediate nodes in this, have to take particular actions on the qubits themselves, and then send messages to other nodes along this chain to tell them what the results of those actions were and what the output is. And so we decided that the direct OpenFlow or SDN-based stuff was not exactly what we needed. So we defined instead what we call the rule set-based operation. And those rules are essentially a single small one-way circuit for when I get a message that says that I have an entangled bell pair with another node, then this is what I'm going to do with it. Okay? And that set of rules can support conditional operation in this, but it's designed deliberately not to be, in computer science terms, Turing complete, because once you start getting Turing complete programs running at every node along the chain, then your ability to prove things about what's going to happen and whether or not it's going to make forward progress just all goes out the window. So we chose to sort of limit the semantics there. A second key innovation, we think, is what we call the two-pass setup, where an initiator and a responder, note that we do not call these source and destination or source and target or things like that, because the primitive that the network is providing here is entanglement, and entanglement is asymmetric. It's symmetric. It has no direction to it, and it doesn't matter which way you're going to teleport data or what you're going to do with it. So The initiator is the one who sends the first classical message to a responder, and this would be very much like a client and a server in a classical network architecture, and says, I want to create a connection with you so that we can share some bell pairs. What happens is that the messages, as they pass through the network, accumulate information about the quality of the links along that path. And then the responder collects all of that information and decides what all of the nodes along the path should actually do, what their role in that operation is, and distributes that to those other nodes. Once you have that, then you have essentially this SDN-based structure, rule set-based structure for how your connection is going to operate. And if you've done a good job of it, then that will all make forward progress, and it will be a reasonably efficient way to create the end-to-end bell pairs. One of the things about this, by the way, because this is not done by a centralized system, is it allows for innovation at the responder. So if you're Google or you are IBM or you are some other company that does this, if your network management software and your responder software is better than your competitors, then you will build better connections with your clients, and that will be a competitive advantage. And it allows for evolution there incrementally, without having to have sort of what's called a flag day in network protocol terms, where you turn off everything and then turn it back on so that you can deploy a new version of the software. I survived the TCP transition that I mentioned this morning. That was a flag day. It's sort of the canonical flag day. We turned off NCP and we turned on TCP. Everything got rebooted. January 1, 1983, the entire internet was rebooted. Not something that's feasible today, right? So we want to enable that kind of innovation as well. So over the course of the last 15 years, 17 years, 20 years, however long we've been doing this, we've worked on the architecture. We have worked on layered approaches to protocols, and our understanding of what the right way to do this is has evolved over time. But you can see in this diagram that this set of nodes, sometimes they communicate with their nearest neighbors and sometimes they communicate with neighbors that are farther away, which is a necessary result of the structure of repeater networks in this distributed communication. That was all the way back in 2009. Routing, I talked about earlier this morning. This was from the bachelor's thesis of Takahiko Sato, who is now an associate professor at one of Keio's other campuses. Multiplexing, I talked about this morning as well. We have also worked on how to do internetworking at the logical level. And this comes from Shota's PhD thesis. So when you have one network that depends, that's a 2G network that depends on the Steam code, and another network that depends on the surface code, how would you create interoperability between those two? This paper, I'll say, I'll let my ego talk here for just a minute. I think that paper should be cited a lot more often than it is. It's really only got, like a couple dozen citations or something, even though it's a decade old. And I think this is ultimately going to be one of the operational foundational papers about how we do internetworking in the quantum internet as that evolves. I don't know, maybe we're just a decade too early. Speaking of which, I'll tell you a little story. Somebody, not long after I finished my PhD, and I think it might have been Chris Fuchs, but I don't remember for sure. And I asked Chris about this last year, and he said, I don't remember saying that, but it sounds like something I would say. Not long after I finished my PhD back in 2006, I was at a conference someplace, and I was at dinner with some people, and I think it was Charlie Bennett and Chris Fuchs and 2 or 3 other people. And Chris said, I read your PhD thesis. I think you're 20 years ahead of everybody else. Well, there's multi-computer architectures that I was talking about this morning. They're finally starting to, it was my PhD thesis in 2006, and they're finally starting to come in, right? Anyway, just an aside. We have also worked on the issue of security in quantum networks. What happens when somebody hijacks one of your repeaters or routers on the network? How much damage can they do to the operational behavior of the network? If somebody hijacks one router or one repeater on the network, can they bring down the entire quantum internet? That's an important question. For the answer, read those papers. We actually have about three papers on the topic, I believe, at this point. Also, some of you may be familiar with the idea of network coding. We worked on that a while back, and we've worked on application protocols for this. In that particular case, that's a topic known as quantum Byzantine agreement. And let's see, so that's sort of what we think of as the key elements in quantum network or quantum internet architecture. Not so much at the experimental level, it's really at the architectural level on all of these set of things. And it's taken us 17 or 18 years to get this far with this stuff, but we have, hence the slide title, we have planted flags on every topic we can think of related to network construction and architecture. Any questions on this stuff? I know that's the 6 or 8 minute view of this. Yeah, where'd the mic go?
I know, so I'm gonna read the paper for hijacking a repeater, but can you summarize how you measure the impact of a repeater inside a network?
How we measure the impact of this? Well, ultimately what happens in this scenario is that there are a set of management protocols. This morning I was talking about the 4 major roles of a repeater: create local entanglement, turn that into long distance entanglement, manage errors, and then manage the network. So in the process of managing the network, one of the things you have to do is you have to monitor the state of the network. And it means doing, if not necessarily full tomography, some process that allows you to assess the quality of the operations going on in the network. And one of the key questions is, if that particular node cheats and starts lying about the results of those management operations, can it cause other nodes in the network to decide, you know what, this network sucks, it's not good enough for us to actually participate in? And the answer is, if you create a naive approach to doing all of this, you can essentially sever a large segment of the network from the rest of the network. But it doesn't take very complicated changes to those management protocols in order to actually avoid that particular problem. And so there's a relatively straightforward question or a relatively straightforward solution to that particular problem, but it is something you have to actually do, right? Somebody was actually asking me over lunch about adapting about network-wide security and whether or not it's something we need to architect in from the beginning, whereas in the classical internet, it was not architected into, for example, routing protocols at the beginning. And the answer to that is, absolutely yes, we should learn as much as we possibly can from this 60 years worth of learning that we have done in the process of designing and building the classical internet. So we should. Other questions? All right, let me go on for a few minutes then. So, names I keep saying, Kai Namoto, Shota Nagayama. Who's this guy? There he goes, who's this guy? I think he's even wearing the same shirt. So that's Asuma-san there. So this is the group that founded the Quantum Internet Task Force. When was this? The date should be on this slide. Maybe the font changes overwrote that. Oh yes, May 2, 2019, which I was not in this picture because they did this the weekend my younger sister got married, and every once in a while I succeed in prioritizing family over work. So Edison, you're not in that picture, are you? You weren't there at that time? All right. So now let's start talking a little bit about how we're going to actually get to standards. And this plus the next set of slides are going to cover some of this. This is Wojtek Kozlowski, who did work at TU Delft and now works for SURF, which is the Netherlands National Research and Education Network provider, right? Are they the REN in the Netherlands, right? So Wojtek works for them. He and I co-chair what is known as the Quantum Internet Research Group, QIRG, which is part of the IRTF, the Internet Research Task Force. And I'll show you a little bit more about that in a minute. You should all get on the mailing list for QIRG. There's no reason not to. We send out an average of maybe 1 email a month or something. So it's not like it's going to be a huge burden, but the next meeting of the group will be coming up soon, and I'll talk about that in a little bit. The output of the Internet Engineering Task Force, the IETF and the IRTF, can be documents that are known as RFCs. And the name RFC stands for Request for Comments. You remember this morning I put up a slide and I had one picture of me with an old guy and I said, I'm gonna ask you about this guy later. That's a guy named Steve Crocker. Steve Crocker wrote RFC #1. He's the guy who created the term RFC back in 1969. And so ever since, the documents that control the behavior of the internet are known as RFCs, or that define the behavior of the internet. So this is our RFC 9340, 9340. There are about 10,000 documents now documenting the behavior of the internet as a whole. So this one describes architectural principles for a quantum internet. It's pretty much vocabulary and concept descriptions, as opposed to any sort of standard. But in the long run, we actually want to get to standards. I'll talk about that a little bit more in a minute. Finally, our group, products you can use. We're not just pretty faces, right? Obviously. We have online courses and textbooks and simulation software and a bunch of other stuff, right? So if you have, everybody in this room is well beyond this particular state, but if you have friends and family or younger students in your lab or whatnot, this course we made all the way back in, 2017 or something. It's an online course for beginners, suitable for high school or for first-year undergrads. It's about 10 or 15 hours worth of work. More recently, that's Mikkel and me, and we've created a set of 3 online courses with more coming on quantum communications as part of the, that says, the quantum human resource development education stuff up there at the top, right? The first course of that is now turned into an open source textbook, which is on the archive, and we are in the process of finalizing a contract with a publisher to publish an actual paper version of this. Basic undergrad level textbook on quantum communications, 300 and some pages. So there's that. You should read all of these things. And then ultimately, in our project, this is the set of things that we are working on, the specifications that describe the behavior of the nodes. Remember earlier I had that big matrix with the different kinds of nodes versus the different kinds of networks. Well, every different kind of node is going to need its own specification that describes its behavior, whether that's an entangled photon pair source or a measurement node or a full computational node. You need to worry about how to set up the distributed connections, this rule sets, all of this sort of stuff. And this part in pink over here is photons. And I'm very interested in how we're going to go about standardizing photons. George and I were talking about that yesterday, right? So that's an important and interesting task that must be completed in order for us to have a thriving ecosystem where multiple hardware and software vendors exist, and those things can be bought and plugged together. So software. Today, we did not get around to actually using QUISP, but QUISP is the quantum internet simulation package, which my group has been developing for about 7 or 8 years now. Although development is actually currently pretty quiet. If you look at the GitHub repository, you'll see there aren't many check-ins in the last 18 months or so. But it is ready to use for a number of purposes, although in order to extend it and add additional things, you need to be fluent in C++ and figure out how to get the packages that it's built on top of actually installed and running on your machine, and that's a tremendous pain. But you can run simple demos of this directly in the browser. Anybody know what WASM is? W-A-S-M? Nobody here's enough of a webhead to know what WASM is. So WASM is the web assembly language, and it's basically a way to compile a program so that it can run efficiently inside the web browser. And this massive system of OmNet++, which is a classical network simulation tool, plus a few tens of thousands of lines of code for QUISP itself, that will compile into a WASM file and actually run directly in your browser. So on the GitHub repository, there's a link you can click and it will load 30 or 40 megabytes into your web browser and start something up. If you are working in the lab, many of you have probably bought equipment from Thor Labs and other people. And one of the great things about Thor Labs is that their catalog evolves very slowly, right? You can still buy something that was designed decades ago, but that also means that that whatever software and control there is for it also was designed decades ago. And it's not always interoperable, and it's not easy to use, and it's underdocumented, and yada, yada, yada. So we have created a set of software known as PNPQ, Plug and Play Quantum. And if you use Python, all you gotta do is pip install PNPQ, and it'll install. And that will give you nice Python interfaces with testing and with documentation, because we try to be good software engineers. And the guy who's leading a lot of this work is a guy named Andrew Todd. And Andrew has a couple of decades as a professional software engineer. So he's really cracking the whip on the students to make sure the testing and the documentation is all good. But you can do this to run wave plates and switches and polarization controllers and optical delay lines. And it's extensible, and we're happy to have contributions to it to anybody who wants to contribute and add to that. We think it will make your life better. A second package is the time to digital converter or timestamp software. If you have a multi-harp from this particular vendor, from the PicoQuant multi-harp 160 is the device we've got. This is a set of driver software that will collect the data off of that for you, and it is also open source. This is implemented in Rust. And both of these were released just 3 weeks ago, right before QCE, just to make the world a better place. That's pretty much it. Let's see. The next IETF/IRTF meeting will be in Montreal in November. I will be there. We will be having a QIRG meeting. Oh, I got to get the request for that meeting put in. We are happy to have people who want to join and attend that. And also, FYI, I am editor-in-chief of the IEEE Transactions on Quantum Engineering, and I am happy to have your contributions. And from senior people also, I need more associate editors. So if you want to contribute to contribute to the journal that way, I would be delighted. And that's about it. Let's see. By the way, I took that picture. One of my hobbies is astrophotography. Let's see, any questions about this stuff? Then we got about 15 minutes. I want to talk a little bit more about standardization after this. Questions about general networking, wide area networking, other contributions. Yeah, where's the mic? Can you see the screen from back here? Not really.
I've got the slides on my computer. Surely it's in some ways, I guess you can argue about some of this stuff, but like, especially for photons, a bit early to think about trying to standardize them, right? Because there's so many different potential technologies for all sorts of photon sources, quantum memories, etc. And also, yeah, like even optical transduction between different wavelengths is, you know, when quantum information is lossy and challenging. And
somebody I was talking to in Albuquerque, who were we talking to in Albuquerque about this? Were you in that conversation? Maybe, maybe not. The people we were talking to in Albuquerque, somebody was saying that the right place to begin the standardization process is basically at the top of the stack, which is actually kind of counterintuitive in one sense. But the network management stuff, turns out that for those of you who've never run a network, network management is an extraordinarily complex endeavor in its own right, and there are many complicated tools for dealing with it. And if we can get that stuff right up front, it will make a huge amount of difference in the total amount of effort that has to get put into that over the coming decades. And so that's actually a good place to start. And I had that on my list of things to do, but I hadn't really thought of it specifically in those terms. And so actually that conversation, and I wish I could remember who it was with, really sort of changed my own view of that. But the photons, is it too early to standardize those? Yes. Should we do it anyway? Yes. So in fact, I think the first step in that is not defining you will use 871.4 nanometer wavelength and your wave packets will be exactly this long. Instead, what we need in the first stage is we need to learn how to describe those. We need to learn how to write down the specifications for those things such that you can look at the specification for different nodes or different pieces of equipment and know whether or not they are likely to interoperate with each other. And that doesn't mean there's going to be one standard photon. There's not going to be one standard photon that everybody in the world uses forever after for the foreseeable future, and I would say probably ever. But I think in the long run, we'll settle out on a small set of those sorts of things, and having a shared language for how those are described is a good thing. And I think we can and should get started on that process basically today. Although, you know, most of our work so far has really been sort of at the middle working out. I am concerned about that photon layer as well. And that management layer is such an important insight. You know, I'm really glad I had that conversation. Other questions? All right, let's go into the last little segment here on standardization. In fact, talk about this a little bit more. So I mentioned early this morning that some of what you're getting today is really basic stuff and some of it's pretty advanced. It's sort of a mix. So I hope all of you have gotten something out of what we've done today, and I hope most of you feel like it has been a worthwhile several hours here. We covered the very basics of teleportation, purification, entanglement, swapping, and then we've also done some pretty advanced stuff in the network architecture. Arguably, this particular thing should be the kind of thing that winds up the week, winds up the 10 days. But unfortunately, I'm only here for a couple of days, so I have to leave tomorrow night. So we'll do it while we're here. And over the course of the next week, you should think about some of the things that we've said over the course of the last several hours, including this particular bit. So, writing specifications is the kind of thing that's non-trivial. People who don't have direct experience in working on it really sort of seriously underestimate how much work it is, just outright work, and how hard it is to do the negotiations and make the agreements with other people and bring everything together. It's the kind of thing that takes a tremendous amount of maturity and experience. It's a pretty substantial task in its own right. And its importance should not be underestimated. So that ARPANET that I was talking about earlier, the equivalent of routers, they weren't exactly routers in the modern sense, but the devices that connected to computers were a thing called IMPs, interface message processors, built in 1969 by a company called BBN. This is 1978. This is almost a decade later. This is the operations manual and specification for an IMP, and it's 237 pages, okay? This is something, you should all find a copy of this and read it. Although it turns out that finding copies of it's actually a little bit of a hassle. It's one of these things that's sort of gradually fading into obscurity. This is the original specification for Ethernet. Actually, this is version 2, it says, yeah, version 2.0, November 1982. This is what's called DICS, Ethernet, Digital, Intel, and Xerox. If you don't know, the basic idea of Ethernet was actually created at Xerox PARC, the Palo Alto Research Center, in the mid-1970s. And the original version was 3 megabits. This is the 10 megabit specification, which was the first thing that was really sort of productized. And it used a coaxial cable instead of, you know, twisted pair or Ethernet or a radio or anything. This specification is only 113 pages long. It includes everything. It tells you physically about the characteristics of that coaxial cable. It tells you about the allowed rise times of the signals, the voltages on this, the physical connection of that cable to a device called a transceiver. It tells you about the packet format, about addressing, about the CRCs, the cyclical redundancy checks that are sort of the error checking stuff that's on the packet level. It's all there, and it's only 113 pages. It's amazing how much is in that. Internet nodes, as I said a little while ago, are defined essentially by RFCs. And this is sort of a basic set that you would need in order to have sort of a functional network. All of these are from, well, so this one's 1981. That's the TCP specification. They're all from around the early 1980s. TCP specification, 85 pages. The IP specification was only 45. It's really pretty remarkable, it's so short. 2 documents on the host requirements, the things a node needs to do in order to connect to the network. It has to have this set of capabilities in order to connect to a network. Somebody had to write this stuff down, right? And then OSPF v1 was 107 pages, and you also saw OSPF2 v2 a little while ago, and that was 237 pages or something, right? So these are all sort of the early stages of specifications of a network, and it's still several hundred pages of stuff that was negotiated among very smart people in working for a variety of companies and universities and other national labs and other organizations, all with competing agendas, and they came together and created this shared understanding of this structure, right? So it's an important task. Here's a flow for how I see development of protocol, and this is true for both quantum and classical stuff. You begin with some sort of basic idea and some sort of simple analysis of this, and you go from there to some sort of specification, written specification for how the protocol should work, which you may augment with both simulation and implementation, where things in sort of the right-hand side of this are addressing the scalability and breadth of what's going on and stuff. And the left here is confronting and solving the real-world problems in real systems. So from an implementation, you go to lab deployment. Somewhere in all of this, you've got to have testing of all of this. You may actually go from simulation to what's called emulation, where you plug in, you have a network where the pieces of the network are mostly real, but some of them aren't really quite real. They actually run sort of some sort of simulation, some sort of emulated behavior, but that allows you to go one stage more toward reality than simulation, and that's called emulation. And so that can contribute to an implementation as well. Eventually, that specification, you hope, will reach ratification as a standard, and you get to not only to test bed deployment, but to production deployment. And just in terms of the vocabulary here, we, including Shota and me and the others, we've gotten in sort of the bad habit of calling our network in Shinkawasaki a test bed. It's really more of a lab deployment. A test bed is something really that other people can use and that exists in sort of a more real environment than a laboratory. So we call it the test bed. It's not really a test bed in that sense, but eventually gets you to production deployment for these things. All of this takes a long time, right? It also takes a lot of people. This is the set of things I pointed you to a little while ago. The green ones are actually available already in draft form. This one over here on the left, I know you can't read the little tiny stuff there, but that box is a document we call the timing regimes, which is taking us that first step toward understanding how the network layers should be split apart and what the relative responsibilities are. So what happens at the nanosecond time scale versus the millisecond time scale, and how does that affect which things need to be done in hardware and which things need to be done in software? That one's available. The document on distributed connection setup and rule sets are also both available, and both also probably substantially out of date relative to what our current thinking is. So they need to be revised. But all three of those are available on our public GitHub repositories, and we would be happy to have comments on those. So I already talked a little bit about IETF and IRTF. Let's see, do I have the next slide? Yeah, here we go. Let me talk about that in a minute. So the IETF produces the standards for the internet, although not everything is a standard, which I'll talk about in just a second. And the IRTF is the research arm of it, essentially. This is a famous quote by a guy named Dave Clark, who's a professor at MIT. We reject kings, presidents, and voting. We believe in rough consensus and running code, and then gradually developing a good consensus, and from that you build a standard. So IETF operates on the work of individuals. There are many other standards organizations where a country gets a vote, or a company pays tens of thousands of dollars to be a member, and then they get to be part of the development of the standard process. IETF and IRTF, anybody can be involved. You're just an individual. Affiliations are identified just to sort of identify potential biases and also potential IP issues, meaning patents and things like that. But everybody is just an individual, and so it's a matter of who you can convince that your idea is the right one, that your approach to doing things is the right way to doing things. Let's see, so I mentioned the QIRG already. And this document in particular, notice that this document, there's nothing controversial about this document at all. There are no arguments about any of this. It was all very cooperative and collaborative work. Wojtek Kozlowski, Stephanie Wiener, Bruno Reisman, Angela Sarakachapote, Marcello Calefi, and Shota Nagayama. And it took us 4 years to develop this and get this actually published and get it through the full ratification process. And it's not a standard, and there was nothing controversial in it. It just took that long, because you go through revision stages and people have their day jobs and lots of things are going on. So we went through 11 drafts ranging from March 2019 to final publication in, well, final publication was January of 2023. And all of these versions, they're all available in the public repository known as the IETF's data tracker. And so anybody can go back and look at any of this history of this. And the archives of the mailing lists are available as well. This is what's going on right now in the Quantum Internet Research Group. We published 2 RFCs, one, the architectural principles, and then the other one is application scenarios for the quantum internet, aimed at bridging that gap between the classical internet community and the quantum computing community. And there's one that's active right now, a draft by Diego Lopez, a multi-plane architecture proposal for the quantum internet. That's really active right now. And if you have comments on it, you can submit those comments on the mailing list, and they will, and if you were persuasive enough, those will get incorporated into the document. And if you have enough of an influence on the document, you'll get named as an author on the document. There is, by the way, on these RFCs somewhere, I don't have the link on off the top of my head, but a lot of these are designed or created by people from industry, but people from academia do contribute to these. And getting an RFC published is actually a big deal. It's not something you should do just to get an RFC published, but it's a contribution to actually making the operation of the internet better. And they are as valuable and more work than a typical peer-reviewed paper. So those RFCs can be one of several different statuses. They can be informational, experimental, they can be proposed standard, draft standard, or internet standard, or best current practice, or historic. So there are a bunch of different statuses. And then finally, yeah, let's see. That's about it. I highly recommend this book by Dave Clark, who I just mentioned a minute ago, Designing an Internet. And also, for those of you who need sort of a broader education, my own blog posting from several years ago on an entire bookshelf for quantum native engineers. And that's everything I had. It's now 3:32. We can take one or two more questions before we take a break. What other urgent, burning questions do you all have about this overall issue of quantum internet architecture and standards for the quantum internet and everything else? Anything? Somebody's got to have a question, right? All right, Joshua, yeah. You can walk it over to him. You can both get some exercise. Yeah. Turn it on and give it about 3 seconds.
Okay.
There you go.
I don't really know how to ask this one. So there's the specifications for like this, like protocols, like, and then you have this platforms, like physical platforms, and of course, you'll have to wait until the platform matures in order to update your essentially your specifications.
Right.
Like, but how does it affect like waiting for this maturing like protocols and maturing like your platforms, and then with developing this like specifications?
So that's actually a good question. And there are two very different philosophies on that. One is ours, well, ours meaning internet, meaning the internet-oriented folks, IETF. IETF people have sort of this informal rule that nothing should be a standard until there are at least 2 interoperable implementations of it. So the development work is going on at the same time that the specification work is going on, but you should not declare we're done with the specification and start calling it a standard until you have multiple independently created systems that were developed using this standard, and that tells you that the standard is complete enough that that it specifies enough of the characteristics that they're going to be interoperable. An alternative approach is the approach taken by 3GPP, which is the international organization that creates standards for cell phones. Particularly, it was the 3G protocol project or something. I forget exactly what it was. And those specifications, if you put them out, they would fill this table. They're huge specifications. And in the front of each one of those, it says, this standard has not been approved yet, so you are not allowed to implement it. And so they were trying to do all of the design work up front before any implementation happens. But that's not reality. You know, nobody can do that, right? And the big vendors they know that they can't wait until the standard is ratified to start doing development work, because if they do that, their products are gonna be 10 years late, right? And so it says, don't implement this until the standard's ratified, and it's all implemented by the time it gets done anyway. So there are different approaches to that, but fundamentally both evolve over a pretty long period. And it's now 36 after, so I think David wants to wind up, and as I've said a couple of times, I'll be around for about the next 24 hours or so catch me and we can talk about all sorts of stuff. And then the rest of you all have a good 9 days. I hope that this has sort of set you on both some high level thinking and covered some of the basics that some of you may have felt like you needed to brush up on. So thank you all for your attention over the last 5 hours or so.